So it's a pleasure to have Ioan come back for the talk, and he will speak about rotational invariance and GFF scaling limit in the 6-vertex model. Ioan.
Thank you very much, Piet. Um, uh, so it's a great pleasure to talk about this. This is a joint work with with several people, but the main part is with Piet, with Hugo Dominique-Copin, and with Karol Kozlowski, who's here. And we just put this yesterday on the archive, so we're very happy to have this out. Okay, so let's get right into it. I'm sorry, I forgot to eliminate this from the previous title, but I'm mainly going to talk about GFF convergence. So let me set the scene and explain the model of interest to us. So we're going to mainly talk about the 6-vertex model that is here on the right. I introduced it last week. For those of you who don't remember or who weren't there, it's simply a model of, you can see it as a model of heights. So you put heights on the faces of the square lattice, and you weigh the difference between adjacent faces is at exactly 1. So it can be plus or minus 1. And you weigh the configuration by C, which is a number, to the number of saddle vertices. So saddle vertices are vertices that, such as this one, that has the same height along both diagonals. So you see 0 and 0 and 1 and 1. Another way of seeing this is via a arrow configuration where you orient all the edges, and each vertex has the constraint that it has 2 incoming and 2 outgoing edges. The 2 are in bijection, so you can see it one way or another. You will notice that among these vertices, there are vertices such as this one or this one that are saddle vertices. The ones that aren't, such as this one, will have one diagonal for which the heights agree and one for which they disagree. And they have a total increment of 2 if you look around. Okay, maybe I should mention I've kind of defined this model very loosely. If you want to define it precisely, you should either work in a domain, in a fixed domain with certain boundary conditions, or on a torus. The graph needs to be finite. What we will do in this talk is we're going to look on Z2, so on the infinite volume lattice, where you can define a Gibbs measure, and we're going to look at this measure with slope 0, which means that it's invariant under inversion of all arrows. This is something that is depends on how you've taken the limit. It's kind of the most natural measure. For instance, if you take a torus and you don't condition it in any way, this is what you're going to get in the limit. I should mention also that the orange thing, which is the heights, are not actually, I mean, I kind of cheated a bit when I said that there's a bijection, there are gradient heights. Meaning they're defined up to addition of a constant. Okay, so you have this kind, but we will ignore that. We'll consider that it's a real height function. You have this height function defined on the whole of Z2, and you're wondering how it behaves. The main conjecture in this setting is that if C is between 0 and 2, this height will start behaving like a Gaussian free field, with a multiplication factor that depends on C. And here's the explicit formula that gives you sigma in terms of C. So what do I mean by a Gaussian free field? So this is an extremely studied model in statistical mechanics. You could see it as a random function indexed by the plane, which has a covariance matrix given by the, which is it's a Gaussian process, and has a covariance matrix given by the Green's function. But the problem is it's not really a function, it's a generalized function. It doesn't have a pointwise value. But for us, that's not very important. I can show you exactly what it means to converge to the GFF. It means that if you look at the height function here that we've defined, I'll call it H, so the one given by the 6-vertex model, and you take H and you test it against some function phi, like a test function. But H, instead of defining it on Z2, you define it on delta Z2. This converges as delta goes to 0 in law to a normal variable with some variance that depends here on phi. And this variance is given by the double integral gxy phi of x phi of y dx dy, where g is the Green function. Here, this can be formulated in domains as well, and it's actually more probably better to formulate it in domains. But for us, it's the full plane Green function, which we normalize like this. So it's just log of the Euclidean distance between x. Okay, so this is what we mean by it converges to a GFF. Notice that in order for this thing to be, so this is just the integral of H times phi on the plane. So for this to be well defined, since H is defined only up to additive constant, phi needs to be, so it's a test function with integral of phi of x dx equals 0. So the average of phi is equal to 0. What I mean by a test function, you shouldn't worry, there are natural classes of functions, but if you get this, for instance, for continuous compactly supported functions, you've already have it. Essentially, it's any sign measure for which this thing is finite. Okay, so this is the main conjecture. I remind you this C that is between 0 and 2, this comes from the fact that the height function, this height function here in this regime is what's called delocalized, meaning it will have variance that, if you look at it on a larger and larger piece of the lattice, converges to, goes to infinity logarithmically, which is coherent with the GFF behavior. When C is larger than 2, the function is localized, meaning if you put, say, zero boundary conditions and you look at it in a very large domain, it's still going to have an average, it's still going to behave very closely to 0, even in the center. It's going to be tight. So it's not going to have the natural fluctuations which you expect of the GFF, and therefore it's not going to present universality properties, for instance, at least not in the regime of zero slope. Okay. So this is one major conjecture for the 6-vertex model, and it's understanding relatively precisely the behavior of the model. I'll explain why I say relatively precise. I am more interested, I mean, generally, what I do and what I've presented last week was the FK percolation model, which I remind you is essentially on Z2, and to link it to the model here on the right, you define it using the diagonals of the lattice. So you either put diagonals between the red vertices, say the even vertices, or between the blue vertices, and then you weigh such a configuration by p to the number of red edges, 1 minus p to the number of blue edges, q to the number of red clusters. It turns out that if p is the self-dual point, then this is almost proportional to square root of q to the number of loops in this loop representation. And what we've seen is that for q between 1 and 4, the phase transition of the model is continuous, meaning there exists a critical measure that exhibits indications of having a non-trivial scaling limit. And what you expect is that the scaling limit is described by a CLE process, which is a well understood and studied measure on families of loops in the plane. yeah, something that essentially is a law on loops like this. And the law depends on the CLE depends on kappa. Kappa is a value that itself depends on Q, and you have a conjectural value for kappa of Q. Okay. And what we've also seen last week was that these two are in a correspondence that is called the Baxter-Callan-Wu correspondence, which allows us to translate delocalization on this side to continuous phase transition on this side. And Q equals 4 corresponds to C equal 2, and these two things were used in this direction to last week to obtain the fact that for Q between 1 and 4, the phase transition is continuous, and for Q larger than 4, the phase transition is discontinuous. Okay. Hope this is a very quick recap of what we've done last week. This time, we're going to really care about this side of the picture. Okay, so let me announce the theorem. Last week, I've talked about this theorem, but didn't have time to actually show you the proof. This week, we will talk about this theorem here, which says that indeed, the full plane 6-vertex model does converge to the GFF, so confirms the conjecture. And I will write here that it's full plane with 0 slope, so that we don't forget it. Okay, there are a few constraints on the parameter, namely C needs to be larger than 1. It needs larger than 1, yes. It needs to be larger than square root of 3, and it also needs to be smaller than 2. So let me explain a little bit about these constraints and about what goes into the proof of this result. So first of all, the constraint C smaller than 2 is obvious. It's, I hope, clearly essential, because what you expect is that if C is larger than 2, the result is false. You know it's false. You know that the height function is localized. So here you're not expecting the same thing. What about the other two constraints? Well, there are several elements that go into this proof that maybe I should mention now so that we know what we're talking about. So we have a certain understanding of the height function, a kind of qualitative understanding of the height function in the regime C between 1 and 2 via RSW type results. So this these results essentially tell you that the height function is delocalized and behaves qualitatively like a GFF. It's also the kind of thing that allows you to take subsequential limits. It's very similar to what you get in percolation models if you're used to this, if you have RSW. Namely, the family of loops has subsequential limits that behave non-trivial. You have a finite number of large loops in an observation box, something like this. So you have similar qualitative statements, and these ones, they require C larger than 1, and this is because of, in certain representations, this is where you get the FKG inequality. So here, you can either work with heights and look at representations in terms of heights, or more like FK-type representations, like the one developed by Piet Lammers and Sasha Glasman, and which we're using in the paper. Okay, so this is why you need C larger than 1, is because you want these tools, this regularity, and so on. And this seems like a fairly important restriction. We don't really have any idea how to do this for C below 1, even though you expect the model to have similar behavior. But maybe we don't have the right representation, or maybe there's some real obstacle, but in any way, we're not close. So finally, why do we need C larger than 3? This is because, than square root 3, this is because we're going to import the result from FK percolation, namely the rotational invariance. So I should mention that you can't really expect this kind of result to come just from qualitative results of the type Aristotle. You need something. You need something to tell you that the scaling limit is of the right type. It turns out that the rotational invariant is almost this something. So what we're going to do is we're going to take the rotational invariance of Fk, or of the supposed scaling limit or subsequential scaling limits of Fk, and we're going to translate it to 6 vertex. So if you take these two elements together, this tells you that there should be subsequential scaling limits for the height function. They should behave qualitatively like GFF, and they are rotationally invariant. And this is already, this rotation invariance is it's a powerful tool. But this is not going to suffice to get the scaling limit. There are two more elements that kind of go into the proof of the theorem. One of them is the transfer matrix formalism. Representation, I will say. What I mean is there is a representation via transfer matrix, or there are ways of computing quantities you'll see in a minute via transfer matrix for the 6 vertex model, and this is going to turn out to be the right way of looking at the model. That being said, we're using very, very little at this stage of transfer matrix. We're not computing anything. We're using just the fact that it exists, essentially. And finally, another important element is some indication of scale invariance. Meaning there's some sort of indication that if you have a scaling limit or subsequential scaling limit, it should be invariant under rescaling. But it's really, really just a very weak form of this. It doesn't give you the fact that the scaling limit, subsequential scaling limit, is automatically invariant under rescaling. That would be an extremely powerful piece of information. So this glimpse of scaling invariance, this is obtained by computing a certain quantities via the beta ansatz. And I'll explain exactly what it means. So we're having limits that have some very weak form of scale invariance and some rotation invariance. And what we're kind of very, in a very hidden way doing is we're kind of saying that rotation plus scale invariance implies identifying the limit, which is generally accepted as being more or less equivalent to conformal invariance. So there's this kind of meta theorem or functioning of things where if you have a limit that is rotationally invariant and scale invariant, presumably you manage to obtain that it's conformally invariant, and then you identify it. This is really, really just heuristics. It's not at all what happens in the proof, or not what happens in the proof. But I was just mentioning it because I think it's a parallel that is worth drawing. Okay, so as I said, we're going to be looking at the proof of this by combining all of these elements. But maybe I should just mention that it's obviously an interesting question to see what you obtain for Fk from this proof. It's a totally valid question to see what are the consequences for Fk, and you could hope that via the BKW correspondence, maybe you obtain the fact that Fk has scaling limits that are given by CL. Unfortunately, this isn't the case. We don't manage up to now, but we do manage to obtain the values of the 1-arm exponent and the 2-arm exponent for Q between 1 and 4, and the mixing or influence for Q equals 4. So in particular, we, if you remember, I mentioned scaling relations last week. If you have this mixing exponents that we call iota, and the one-arm exponent, you may obtain all the other standard critical exponents. So at q equals 4, it's in preparation, but there will be a proof that critical exponents are what you expect them to. Right. Maybe let me just finish by saying that the BKW correspondence that links these two things is particularly easy for q equals 4. And the lines here, the loops of Fk, correspond to level lines for the height function. So it's very tempting to think that at least for q equals 4, the level lines of Fk will converge to the level lines of GFF, which are indeed CLE 4 as you expected. The problem is the convergence is not continuous with respect to level lines somehow, so or vice versa. So you don't have the fact that if this field of heights converges to GFF, automatically the level lines also converge to GFF. And here I should mention the fact that since our result is in full plane rather than in domains with boundary conditions, this complicates this kind of correspondence very strongly. If you'd have it in domains, for instance, the convergence, at least for q equals 4, you'd probably be able to obtain the convergence of the loops as well for Fk. Okay. So now what I'm going to do is I'm going to go a little bit towards the proof and show you the proof of this, or a very brief overview of what goes into the proof. And I'll start with the element and the computation that gives us this glimpse of scale invariance and the requirement that C is below 2. I wanted to mention C larger than square root of 3. I forgot to mention this. This is simply because we need this rotational invariance input. And this one, the way to obtain it, the way we obtain it is from the Fk representation. And the Fk representation only exists and corresponds to Q between 1 and 4 in the regime C between square root of 3 and square root of 3 and 2. But we really expect that the same proof that allowed us to do this should have a correspondence directly in the 6-vertex model. And so you expect that the rotational invariance of the 6-vertex model should hold for any C between 1 and 2. If you do that, then immediately the proof extends to C larger than 1. So morally, the proof should hold for all C between 1 and 2. It's just this input that we don't have that you may very well think that you can obtain differently. Okay? Are there questions about the result or about anything related to this? Okay, if there are no questions, let me just remind you why we what was this C smaller than 2? So you remember we talked about the free energy of the model with the slope alpha. The slope corresponds to the average height increment between two adjacent faces. And the way we define this free energy with slope alpha is maybe on a cylinder or on a torus, you look at configurations, you look at the probability that configurations have the property that as you wind around the torus vertically, you get a increment of alpha times the size of the torus. So here we're going to look at the torus of size L, and you're going to wonder, okay, what's the probability that as I wind around vertically, I get an increment of alpha times L, for alpha, some number between -1 and 1. And this corresponds to having an excess of right-pointing versus left-pointing arrows or vice versa. And it's an explicit computation shows you that this function f of the free energy is differentiable at 0 for C between 0 and 2, and non-differentiable for C larger than 2. And this is what was used to imply that the phase transition for Fk is continuous or discontinuous in the two regimes. It was related to the probability of having this kind of many interfaces, alpha L interfaces, winding horizontally around the cylinder. Okay. And the way we obtained this theorem that I mentioned last week, this one here, is via an explicit computation of the leading eigenvalues of the blocks of the transfer matrix of 6 vertex. Okay, so I'm not going to go into it, but I'm just going to mention that I said last week that f second of 0, in the case where where f is differentiable, due to parity, you have that f prime of 0 is equal to 0, but what is more interesting is f second of 0. And f second of 0 has information about the scaling limit, or should have information about the scaling limit. In Fk, I remind you that it corresponds, this f second corresponds to this constant here, which is the price to pay for having these kind of many interfaces. And it should somehow be related to a probability of crossing. It's not explicitly, but it should. And this is going to be our glimpse of scaling variance, the fact that this f second of 0 exists, which kind of tells you that there is a quantity that has some meaning in the limit and kind of should allow and does allow you to identify the limit. Because this quantity exists and is unique, it means that the limit can't be, well, it needs to be one out of a range. You'll see exactly that. Okay, so now let's try to understand how you do this convergence to GFF. I'm going to take the k-point function, or rather the 2 k-point function of the discrete model. What does that mean? It means you take 4 k-points, and you look at increments along these between these points, and then you multiply these increments and you look at the expectation. I'm taking here 2k even because if you take something odd just by symmetry, you get 0. So only the even moments are interesting. And what you expect or think you would have if you have a GFF convergence is that these moments converge to their correspondent moments for GFF. This is an extremely explicit expression. You can write it out. It's just a little bit complicated to write out, so I'm not going to try, but it's completely explicit. What you expect is that also, I mean, what you should have if you have a convergence to sigma times GFF, if you have here a scaling factor. Since this is a moment of order 2k, you expect sigma to appear into the power 2. Okay. So this is what you would like to have if you think you have convergence to GFF. And it turns out that this is sufficient to obtain convergence in other in the sense that I've drawn before. So this is what going to be our goal. Is anybody interested or to see what this expectation should be? Or you kind of see? Basically, what you have is that you have these guys, they form a Gaussian vector, and the covariances between them are given by the green function. So you just need to write this out. Yeah, I don't know. If somebody wants, I can write it, but I'll maybe write it in for the k equals, for the 2-point function, which is the one that is going to be interesting to us the most. Okay. So here are a few observations about this kind of convergence. First of all, it's something that I mentioned, is that this regularity statement, this convergence here of the moments is going to be sufficient to imply a GFF convergence. And this is a very weak statement. It's not something that we're going to be concerned about. but it comes from the regularity of the discrete field that tells you that you can basically swap integrals. Yeah, and it gives you this. It tells you that if once you have this, you have convergence in more or less any way that is reasonable to expect. Regularity also tells you that you have compactness for this kind of convergence, so that you can always take subsequential limits as delta tends to 0, so that you have convergences for these quantities towards something, but not clear towards what. Then we're going to have the glimpse of scaling variance, which essentially tells you that if you have such a convergence, if you have convergence to GFF, then you know what the sigma should be. The sigma is related to something, namely to the second derivative of the free energy at slope 0 via a formula, which I hope is this one. Okay, so if I tell you there's GFF convergence, this theorem tells you, and F second tells you what the variance should be. Then there's a third theorem, which is a little bit more complicated to understand, which is the fact that if you have this kind of convergence for the 2-point function, then you can obtain it for the k-point function. This is delicate. This is something that is really deep in our proof, and it's a consequence of or the technique is basically amounts to extending harmonicity. I'm talking about harmonicity because this function here, the moments of the Gaussian free field should be harmonic in each UI, as long as all the UIs are different. It has a different poles when the UIs become equal. Okay. So this this thing is basically, yeah.
Extending harmonicity of what here?
So it's basically, this is what I wanted to say. It's you extend harmonicity from k equals 2 to k larger than 2. What I'm saying is, if you have this kind of convergence for k equals 2, then you know that for k equals 2 for the 2-point function, you have harmonicity, and then you can extend it to the k-point function or 2k-point function. All right. I should have written. So the first one is just the regularity. The second one is the glimpse.
If I may, I also have a question.
Yes.
So regarding the third point, so the limiting guy in that case of GFF, and one can compute using Wick product formula.
Exactly, yes.
So on the discrete level, you have something. So does extending harmonicity is kind of a variant of a Wick product formula on a discrete level?
No, it's not. No, it's not. I don't know. At some point a while ago, we were wondering if you can get the Wick rule directly in the discrete, which would be an amazing thing if you kind of see it appearing in the discrete. But unless I'm mistaken, there's no direct way to see it in the discrete.
Okay, thank you.
So it's a little bit different. You basically just you'll see it's very artificial, actually, the way to get our harmonicity.
Okay, thank you.
So no, it's unfortunately no. That's the answer. And the final and most important and key somehow theorem is this one, which says that there are two. It's a sort of dichotomy, which tells you that for k equals 2, either you for k equals 1, so for the 2-point function, you either have a GFF limit, Or if not, then you have subsequential limits, maybe some GFF, maybe some not GFF, but you have at least two different GFF limits. Well, I mean distinct, I mean with different variances. And you'll see that if you confront this computation of the variance with this theorem, and you see that, so first of all, if you have this kind of convergence for k equals 2, then you have it for all k. And then you have basically the limit. So either you're in this case, you have a single GFF limit, which is what you want.
Sorry to bother you, Ioan, but
yeah,
in these equations, it's k equals 1, right? Because k equals 2, you're talking about the 2-point function.
Yes.
Sorry about that.
Thank you. Yeah. So so here in this main theorem, the dichotomy tells you either you have a single GFF limit, which is basically what you want to prove. This is what we want to prove. Or you have subsequential limits that are different GFFs, but this isn't possible because you know that you have a single possible variance for the GFF. And this says the second case here is impossible.
Got a little bit lost. So could you just re-explain the contradiction there? I just got confused.
So the second point is telling you that you will have subsequential limits, a priori many types of subsequential limits, but among these there are at least two different GFF limits. So GFF limits with two different values of sigma. And this theorem here tells you if there exists even a subsequential GFF limit, the sigma is this one.
Yeah, okay, great. Got it. Thanks.
Okay. And these, this really acts as a glimpse of scaling variance because essentially the contradiction here comes from the possibility of having a limit that is not scaling variant and whose, if you take the limit and then you take the limit of the limit as you scale in or out, these two scales are different. Those two limits necessarily are GFF, but different ones. So it's really, you don't see it in the way I explained, but this is really something that tells you that your limit should be scaling variant. More. Okay, so we agree that if we combine these four theorems, we obtain our result, I think. Yes. So my goal now for the amount of time that I have left, which is, I'm not sure, maybe not so long.
You have about 15 minutes.
Okay, so my goal now is to try to give you some elements of these proofs. Now I can skip ahead and prove a different one of them, but I was thinking of focusing mainly on this one, which is the main theorem. By the way, I forgot to say, but this is essentially where rotational invariance comes into this theorem. Yeah. Okay, do we go ahead with this? Let's try. So this is what we're going to try to prove, the fact that the 2-point function has either a GFF or a limit which corresponds to GFF, or there are multiple subsequential limits of which at least you have two different distinct GFF limits. So I'll start by explaining a little bit about the transfer matrix and the transfer matrix representation. So we're going to go back to the cylinder. I hope you will accept that if this is the torus actually, which has a length, horizontal length m and a width L. If I take m and L to tend to infinity, first m to infinity, then L to infinity, this converges to Z2. And what I mean is the sixth vertex will converge to the infinite volume sixth vertex. Okay, this is something I hope you can accept. You don't even need to know that this happens for all L and M. Just subsequentially is sufficient. Okay, so we're going to take this limits as M and L tend to infinity, but we're going to think about the torus because it's where the transfer matrix is best defined. So you remember there's a transfer matrix T, which I'll call T pi over 2. This is the transfer matrix. And it essentially encodes, it goes like this. It essentially encodes it's indexed by potential configurations on vertical rows of horizontal arrows. And it encodes the energy or the probability of passing from one arrow to the next, from one arrow configuration to the next. So if you want to compute the partition function of the model on a torus, you just take the trace of the transfer matrix to the power m. But we don't want to compute the partition function. We want to compute height increments and correlations of height increments. So what do you do? Well, what you're going to do is you're going to compute correlation of height increments. So here I have four points that are ordered like this, horizontally. If I want to compute this, I can basically compute just increments or correlations of edges. Okay, because when I sum these up, I get correlations of height increments. And by edges, I mean, you should really think about, these are edges between centers of faces. And what I'm wondering is how the increment of height here is related to the increment of height here, which is essentially how this edge is correlated with this edge, or the arrow there. This is what I care about, okay? So how do you do this for two edges? Well, it's not so surprising if I write it. What you're gonna do is you're gonna say, look, I'm going to look at this, okay? I'm going to look at the transfer matrix. I'm going to have something like transfer matrix to some power. Then which I imagine it's coming from here. Then I'll insert a sort of operator that will give me the direction of this arrow. Then I'll have the transfer matrix again to the power x, which x is the distance, the horizontal distance between these. Then I'll have a new operator. Notice that these two operators are not necessarily the same ones because one gives me the direction of this arrow and one of this arrow. So maybe I'll write here s tilde. And then I have again the transfer matrix pi over 2 to some other power. So these powers are, and then I need to take the trace of this. This is basically going to give me the covariance between these two edges. And then I need to sum this up. Yeah. As I take L to infinity, maybe I should say, I mentioned it, but last week, but maybe it wasn't clear. The transfer matrix or the main block of the transfer matrix, which you can assume we're working with, is a Perron-Frobenius matrix, meaning it has one main eigenvector with largest eigenvalue, and all the eigenvalues are smaller in absolute value than this main eigenvalue. They're also all real because it's a symmetric matrix. Okay. So now as m tends to infinity, basically when I look at this trace here, this transfer matrix, I can pass it on to the other side. So let's just eliminate it from here and just put it here. And it's essentially to the power m minus x. And as m tends to infinity, what you want is you just want to have the main eigenvector on this side here. Okay. Let me also mention that as you look at this, you don't like this. You don't like this kind of expression because there are too many matrices here. There's the matrix T, that is the transfer matrix. There's the matrix S, and there's the matrix S tilde. And S tilde can be anything, basically, because it can be any shift of S. So in order to limit the number of matrices that you work with, what you can write is you can say that S tilde is nothing else than S, but it's multiplied, it's conjugated by a shift, a horizontal shift of the torus, which I call a vertical shift of the torus, which I call T. So I'm not sure where this thing is, but it's probably Y and minus Y, where Y is this thing here, this distance. So basically what you're saying is that getting the sign of this arrow is the same as getting the sign of this arrow, but you turn the torus vertically, you take the sign and you turn it back. This is what I'm saying here. Okay. And this is nice because now I have only 3 matrices that give me everything. I have the matrix S, I have the matrix T0, and I have the matrix T pi over 2. T pi over 2 is the transfer matrix. T0 is the shift matrix, and S is the indicator of an edge, the sign of an edge. Okay, so you're computing traces of this kind, and another good piece of news is that these two guys commute. So these two matrices, they commute. And so they're co-diagonalizable in a orthonormal basis, actually, which we call V0, V1, etc. And these are the eigenvalues corresponding. So when you compute this trace, it's very natural to look at it in this eigenvalue of, in this basis of eigenvalues of, and eigenvectors of the two transfer matrices. I put T pi over 2 and T0 because T0 is actually an instance of the transfer matrix, but with an angle 0. It's, if you look at the isoradial representation, this is what it corresponds to. But you can just say that I'm crazy and I want to call the transfer matrix T pi over 2 and the shift matrix T0. It doesn't matter what it is. Okay. By the way, the fact that they commute is immediate if you look at it. Yeah, it's a very clear state. Okay, so what do you get if you sum this up? I'm going to immediately just show you the formula because I can't compute it. But maybe the only thing that you can look at is that this guy here and this guy are not really going to play any role, because as you take m to infinity, the only contribution is going to be when you're basically having here the vertex V0. Right? It's going to pick up some eigenvalues, which if you normalize your matrices, these eigenvalues are going to be 1. So V0, as you come as you multiply this with the V0 here to the left, this guy has no effect on V0, it's just the eigenvalue 1. Then S is going to split V0, is going to be a sum of C0j Vj. Then you're going to pick up eigenvalues here corresponding to the Vj. So lambda 0 of pi over 2 and lambda j of pi over 2 and lambda j of 0. And then S here is going to get you back to V0. And all the other contributions are going to be negligible as t tends to infinity, as m tends to infinity, so as the length of your cylinder tends to.
Why is
Okay.
Why is the T0 to the minus y negligible as m goes to infinity? There's no m dependence.
No, but so basically what you have here is you start with a vector. If you compute a trace, you start with a vector and you need to finish with the same vector. And if you start and finish with anything else except V0, this guy's gonna completely kill it. So what you get is you get an expression of this sort. These guys, so you have these eigenvalues of lambda j of pi over 2 and lambda j of 0 that appear. you see you have exactly the kind of expression I had on the previous slide here that comes from this, sorry, from this. And because you sum these expressions, you get these sort of expressions, which are essentially just sums of this. Okay. And these CI, these guys are things like SV0, Vj. These are the weights appearing as S splits one eigenvector in the basis of the others. S is obviously not commuting with T, so when you apply S to eigenvectors, it completely messes up what makes it jump to different eigenvectors. Okay, this is the kind of expression. This is an exact equality for the cylinder. And so the way you should look at this is this number here is a positive number, and you should look at it as a weight. And you should look at the rest as an integrand. Sorry, with T, right? And it's a function, it's essentially a function, I don't know, f of lambda j pi over 2 and lambda j of 0. Okay, it's a function that depends on x and x1, x2, x3, and y1, y2, y3, but it depends on the eigenvalues. So if you do that, you could just write this as an integral, where you have here a sort of spectral measure. Which is just a weighted sum of Dirac. And it turns out that it's good to encode these eigenvalues not by their value lambda, but by their logarithm. So what you're having is you have e to the minus a is lambda 0, lambda of pi over 2, and e to the minus b, ib, is lambda j 0. You want to encode them like this. Okay, so basically you're putting Diracs at A and B that correspond to this, and the Dirac has this mass. Okay, and then you're summing all. Right. X and Y, x1, x2, x3, y1, y2, y3 are the vectors that are the increments between u1 up to u4. These eigenvalues are all roots of unity, because they are eigenvalues of the shift operator that to the power L becomes the identity. So they're all roots of unity. These ones here, these eigenvalues, they're between 0 and 1. Well, they're between -1 and 1, but let's just say they're between 0 and 1. So A is a positive real. And B is a real number. Okay? Due to this form. I'm cheating a bit for A. It's not really true that it's a real number if you write this, but in the limit it becomes. Okay? And so the whole game of understanding this 4-point partition function, this 2-point function, is to understand this measure. Can we understand how this measure behaves? So if you take limits, you can always do this subsequently. We have regularity, we have properties of regularity of these measures. I'll explain in a minute what they are, but they allow you to have compactness for these measures in a suitable topology, so you can take limits of these measures. So the way you should take limits is you've already taken the limit as the cylinder, as the torus becomes very long. This was done when we eliminated all the other eigenvectors except the main eigenvector. Then you can take the limit as the size of the torus goes to infinity, as the width of the torus goes to infinity. So this is kind of not so interesting, is you get here a measure for kind of the infinite torus. So this starts not being a sum of Dirac masses anymore, but a limit of such things. But you can still imagine it as a sum of Dirac masses. But more interesting, what you do is you take a limit as the mesh size goes to 0. So when you write the thing for a fixed mesh size, you can just write exactly the same equation. You just need to divide all the increments x and y by delta, which is the mesh size, which is equivalent to basically taking the points and taking them very far away. And then what you can do is you can fix x and y and see this this multiplication by delta or division by delta on the measure. So let me just draw a little bit these measures and have an image of what they are. So both all of these measures are measures that are supported on R times R plus times R. So they're supported on this part. They're symmetric under vertical shift. Under vertical reflection, meaning under the transformation AB goes to A minus B. This is because basically whatever happens in B is invariant under conjugation, under complex conjugation. So anything above the horizontal is the same reflected below the horizontal. And if you're in on the cylinder, what you have is you have a sort of sum of Dirac masses like this with different weights, maybe more weight here, more weight here. Okay. And then you look at this as you take limits, and this limit, this second limit here, just corresponds to zooming in to what happens around 0. So this is zoom in around 0. It's a very easy limit to understand. You're basically zooming in to what happened around 0. Let me write the conjecture. So what are the measures that give you the correct GFF 2-point function? They're necessarily of the type they're supported on A squared equal B squared. And if you look at the marginal in A, it has density sigma over A dA. So what you expect is that your measure is actually completely concentrated on these two diagonals. And it has this density. The density is not as important, though you can forget a bit about it. Really what's the main importance is that it's concentrated on the diagonals. So this is what you expect, or this is what will give you that it's a GFF limit. And this density is precisely coherent with this zooming in around 0. It's a density that is invariant under this zooming in around 0. That's the way you do the procedure. Okay. I said that we have certain regularity bounds for this measure. So we know that they're not completely crazy. So the kind of bounds we have are, if you take here any strip between alpha and 2 alpha, you know that the total measure contained in this strip is bounded uniformly in alpha. And you also know that you have no measure here towards plus infinity and minus infinity in B. You know that it decreases somehow. This comes from RSW considerations and the fact that the height function doesn't behave to Y. Okay. So these bounds are things that allow you to take limits of these measures, that allow you to know more or less what is integrable it gives you kind of dominated convergence criteria and so on. Okay.
Just to say, I think you have about 2 more minutes. Is that okay?
Yes, I will try to finish with this. So can you get this kind of can you solve this conjecture using? Ooh, sorry, I realized now I looked at the time. Sorry, I'm very slow. I'll finish very quickly. What can help you to have this to solve this kind of conjecture? Well, the one thing you have is that this function here is invariant under rotations. And now I'm just going to come back to your to the question about Vick rule, which it's not the answer that you're expecting, but anyway. If you look at this function, you will notice that it writes like I of x1 minus x3 plus I of x2 minus x4. Sorry, not x, y, u. u1 minus u3 plus y of u2 minus u4 minus I u1 minus u4 minus I u2 minus u3. Okay, this is you get immediately out of the transfer matrix representation, and this is kind of coherent. This is what you expect for a GFF, and you expect. I mean, it's not so surprising that it's of this sort. What is surprising and what is extremely valuable information is that this I here, that is an explicit function, it only depends on the distance, the Euclidean distance between the points. And this is due to the fact that things are rotational invariant. And what you obviously expect is you expect that I of x is log x minus 1 over 2 pi times sigma. So this is what you expect of maybe sigma squared of I. So the question is, what can you tell about I, or what can you tell about the measure from the fact that it's rotational invariant and that it has good bounds? And I'm going to finish by saying that I've written here basically an instance of this, the fact that you have a rotational invariance. The corollary of this, or the theorem that you get out of this, is unfortunately not that the measure is concentrated in diagonals, but is that it's concentrated below the diagonals. So this tells you that all the measure is concentrated here, on the diagonals or below. And you'd think, okay, so you're basically there. I mean, A, B, they play more or less the same roles. If you look at the formulas, everything looks symmetric. So presumably, if you manage to prove this, you can also prove that B is larger than A, larger or equal than A, almost surely. And then you have that the measure is concentrated on diagonals. And this essentially tells you that it has the correct form and that your limit is GFF. Well, unfortunately, this isn't the case. We can't manage to obtain through the same technique that you have the opposite bound. But what you do get from this is you get this corollary that there exists subsequential limits for which A is equal to B almost surely, almost everywhere. And these are these GFF limits. And what you also have is you have a sort of mass for the limit, which tells you the sigma. And either you have a unique limit that has this, or you have two separate limits that have two different masses of this type. And this gives you the GFF limits, and then you can go back from there. Okay, I'm sorry that I took so long on this and that I didn't have time to tell you about the rest, but I'm going to stop now. And I apologize to Martin.
Thank you, Aaron. Any questions? I have one. So you said that there exist subsequential limits for which A is mod B almost everywhere, and these are the Gaussian ones. I'm just slightly confused. So then you could have subsequential limits which are really inside the interior, and you have non-Gaussian, or
Yeah, so I don't have the formula here, but there are, for a very long time, we thought clearly these should be the only ones on A equals B on the diagonals. And then Carol came up with examples that satisfy all the other requirements. So the rotational invariance requirement, which is essentially equivalent to this equation here. So it satisfies this. It satisfies the bounds that we want, the qualitative bounds, and they're not on A equals B. They're on a different part of the spectrum. I can't remember. They have a formula. They have a very specific form. We think that those correspond to massive GFFs. So you could a priori have, by the way, if you have two measures that satisfy this, then there's some also satisfy. So you could have a mixture of models. And that's when we realize that, okay, well, if you have these and you zoom in and out of such a limit, all your mass disappears. So there's some sort of function of mass. And if you zoom in, you get all the mass. And if you zoom out, you get none of the mass. So that's why you should have two different GFFs in the limit if you have non-GFF limits. Okay. If you have these non-GFF ones, then zooming in and out of them, you get two pure GFFs with different sigmas.
Okay, thanks. Any other questions? If not, let's thank Ioan again. So Martin, are you okay if we take a 5-minute break to stretch legs and then we start in 5 minutes?
Yes.
Perfect.
Thank you. And sorry, Martin,
It's all right. I have
blocked
a
you.
relaxed schedule today, so it's okay.
Good. I don't. So I need to run.
All right.
Okay, bye.
Bye.